Borgund, Norway, 1180 AD. A carpenter drives his axe into a pine log. He's been working this joint for 3 days. No nails, no screws, no metal fasteners of any kind. Just wood against wood, shaped by hand until the fit is so precise that water cannot penetrate the seam. That joint is still holding today. 844 years later, the Borgund stave church stands exactly where that carpenter left it. The walls haven't shifted, the corners haven't separated, the roof hasn't sagged. Not a single nail in the entire structure. Modern contractors look at Viking joinery and can't understand how it works. They've been trained to think in terms of mechanical fasteners, nails that grip through friction, screws that bite through threads, bolts that clamp through tension. The Vikings used none of these. They used geometry. Every joint in a Viking structure was a three-dimensional puzzle, cut so precisely that the pieces locked together under their own weight. Gravity became the fastener. Wood movement became the tightening mechanism. Modern nail-built houses have a structural lifespan of 50 to 100 years. After that, the nails corrode, the wood shrinks away from the fasteners, and the structure begins to fail. Viking houses lasted 500 years. Some lasted 1,000. The Vikings didn't fasten wood. They married it. The technique has a name: Tømmermannskunst, the carpenter's art. And we've almost completely forgotten how it works. Here's what they understood about wood that we've chosen to ignore. To understand Viking joinery, you must first understand that wood is not dead. Modern construction treats lumber as inert material. Cut it, dry it, nail it, forget it. This approach works for decades. Then the building starts falling apart. The Vikings understood that wood never stops moving. The moisture cycle wood is hygroscopic. It absorbs and releases moisture from the surrounding air continuously throughout its existence. This isn't a flaw. It's a fundamental property of the material. When humidity rises, wood absorbs water vapor. The cell walls swell. A 12-inch log can expand by a 1/4 inch across its width. When humidity falls, wood releases moisture. The cells contract. That same log shrinks back. This cycle never ends. A piece of wood that's been in a building for 500 years is still responding to humidity changes today. Modern fasteners fight this movement. A nail driven through a board creates a fixed point. When the wood swells, it presses against the nail. When it shrinks, it pulls away. Over thousands of cycles, the wood fibers around the nail are crushed and torn. The hole enlarges. The grip weakens. Eventually, the nail holds nothing but air. The Viking solution, Viking joinery, doesn't fight wood movement. It harnesses it. The principle: cut joints that tighten as wood shrinks and loosen as wood swells, then orient the wood so that seasonal movement pulls the joint together rather than pushing it apart. This requires understanding wood grain at a level most modern carpenters never learn. Grain orientation. Wood moves differently in different directions. Along the grain, parallel to the fibers, wood barely moves at all. On a 12-foot log might change length by a 1/16 of an inch across its entire lifespan. Across the grain, perpendicular to the fibers, wood moves dramatically. That same log might change width by 1/2 an inch between dry winter and humid summer.
As we move closer,
radially from center to edge, and tangentially around the growth rings. The movement rates differ by a factor of 2. Viking carpenters knew these relationships intuitively. They oriented every piece of wood so that its movement would work with the structure, not against it. Selecting the right tree. The process began in the forest. Vikings didn't cut just any tree. They selected specific trees based on growth characteristics, grain pattern, and intended use. For structural timbers, they preferred trees that had grown slowly, tight growth rings indicate dents, for strong wood with minimal movement. For planks and boards, they selected trees with straight grain running the full length of the trunk. No twists, no spiral growth that would cause warping. The selection happened in winter, when sap was down and moisture content lowest. A tree cut in January starts its building career already partially dried. After felling, logs were often left in place for a full year, seasoning under bark while the wood slowly equilibrated with atmospheric moisture. Only then did shaping begin. This is materials science masquerading as folk craft. The tools Viking carpenters worked primarily with axes. Not the heavy splitting axes of modern forestry, precision tools with thin, curved blades designed for controlled shaping. At the broadaxe, a wide blade with one flat face, could shave wood surfaces smooth enough to require no sanding. Skilled users achieved tolerances within a 1/16 of an inch. The hand axe, a smaller tool for detail work, carved the complex angles of joints. The auger, a spiral drilling tool, created holes for wooden pegs. The chisel, for cleaning corners and flattening surfaces. No power tools. No measuring tape in the modern sense. Vikings used body-based measurements. The EL, forearm length, roughly 18 inches. The thumb breadth, the hand span. Yet their joints fit with precision that modern machine-cut lumber rarely achieves. The secret wasn't the tools. It was the process. Viking construction used 4 primary joint types, each designed for specific structural functions. The joint type 1, the notched corner, the signature Viking joint. 2 horizontal logs meeting at a corner, each notched to receive the other. The basic concept seems simple. Cut a semicircular depression in the bottom of one log, set it over the round top of the perpendicular log below. The execution is anything but simple. The notch must match the curvature of the receiving log exactly. Not approximately, exactly. Any gap allows air and water infiltration. Any excess tightness prevents the log from seating fully. Viking carpenters used a tool called a scribing compass, 2 pointed legs connected by an adjustable joint. One point traced along the lower log's curve, while the other scratched a matching line on the upper log. The notch was then cut precisely to that scribed line. But here's the critical detail most modern reconstructors miss. The notch was cut slightly undersized. A notch that fits perfectly when cut will become loose as the wood dries. The Vikings cut notches that were tight at initial assembly, sometimes requiring wooden mallets to seat the logs. As the wood seasoned over the following months, it shrank onto the joint. The fit tightened. By the time the building was a year old, those corners were effectively welded together by wood compression. Joint type 2, the dovetail, for joining horizontal members to vertical posts, as in stave church construction. Vikings used dovetail joints. The dovetail shape, a trapezoidal tenon, wider at the end than at the base, fitting into a matching mortise. The geometry is self-locking. Once assembled, the joint cannot pull apart along the axis of the tenon. The angled faces mechanically interlock. Viking dovetails typically had angles of approximately 75 to 80 degrees. Shallow enough to provide strong mechanical lock, steep enough to be cut accurately with hand tools. The fit tolerance, essentially, 0 gap. Dovetail joints were cut to require light mallet driving for assembly. The wood-to-wood contact across the entire joint surface distributed load evenly, preventing stress concentrations that cause failure. Joint type 3, the scarf joint. When logs weren't long enough, Vikings joined them end-to-end using scarf joints. The scarf, an angled splice, typically at a ratio of 1 to 12. A 12-inch thick timber would have a scarf face 12 inches long at a 12-degree angle. The mating surfaces were cut to match precisely, then pegged together with wooden dowels. Or why the shallow angle? Stress distribution. A perpendicular splice creates a stress concentration. All the load transfers through a small contact area. The wood crushes or splits. A scarf spreads the load across the entire angled face. The longer the scarf, the larger the contact area, the lower the stress per square inch. Viking carpenters couldn't calculate stress equations, but they understood from experience that longer scarfs held better. Trial and error over generations produced the optimal ratio. Joint type 4, the wooden peg, tree nail. Where mechanical connection was needed beyond joint geometry, Vikings used wooden pegs, never metal nails. The peg material, typically oak, harder than the pine or spruce it fastened. Harder material crushes softer material, creating a tighter fit over time. The peg shape, not cylindrical. Viking pegs were typically octagonal or faceted, hand-carved with slight taper. Why not round? 2 reasons. First, a faceted peg has corners that bite into the surrounding wood, resisting rotation. Second, the facets allow slight compression when driven, creating a spring-loaded fit that maintains pressure as wood moves. The hole was drilled slightly undersized. The peg was driven with a wooden mallet, compressing as it entered. The compressed wood then tried to expand back to its original shape, gripping the walls of the hole. This is the opposite of nail logic. A nail creates a hole larger than itself and relies on friction. A Viking peg creates a hole smaller than itself and relies on compression. As the wood around the peg shrinks with seasonal drying, the peg shrinks too, maintaining relative fit. A nail doesn't shrink. The hole enlarges around it. The assembly sequence Viking buildings weren't constructed joint by joint. They were pre-assembled. All components were cut, fitted, and test-assembled on the ground. Each piece was marked with runic or symbolic notation, indicating its position and orientation. The test assembly revealed fitting problems before the building went up. Adjustments were made on the ground, where access was easy. Only when every joint had been verified did the raising begin. This prefabrication approach meant that the actual erection of a Viking building could happen quickly, sometimes in a single day, with sufficient labor. The skilled work was in the months of preparation, not the hours of assembly. In that balance between patience and precision, they made their choice. If you're starting to see Viking carpentry as a lost engineering discipline, you're understanding why these buildings outlasted everything we build today. Subscribe, because we're about to cover the stave churches, the peak of this technology, and why the construction technique almost disappeared entirely.
Built in the 12th
The tallest
century
wooden
without
buildings in
ceiling,
medieval Europe
these
weren't built
towering
with
wooden
nails.
structures have defied the
Between 1100 and 1350 AD, Norwegians built approximately 1,000 stave churches. These weren't simple log cabins. They were multi-story wooden cathedrals, some rising over 60 feet tall, with intricate carved ornamentation and structural engineering that still challenges modern analysis. 28 survive today. Each one is an encyclopedia of Viking joinery. And the structural system stave construction differs from log construction in a fundamental way. Log buildings stack horizontal timbers. The walls are solid wood, simple, strong, but limited in height by the available log length. Stave buildings use vertical posts, staves, as the primary structure. The posts support a framework of horizontal beams, which in turn support the roof and walls. This post and beam system can reach heights impossible with log construction. The Heddle Stave Church rises to over 65 feet. The tallest log building rarely exceeded 20 feet. But vertical posts create an engineering problem: rot. A vertical post set into the ground acts as a wick, drawing moisture up from the soil. Within decades, the buried section rots. The building collapses. Viking builders solved this with a sill system on the raised sill. Instead of burying posts in the ground, Viking stave churches rest on a foundation of horizontal sills, massive timber beams laid on stone footings. The vertical staves don't touch the ground at all. They sit in mortises cut into the sills, held by gravity and joint geometry. Water can't wick upward through horizontal grain. The sills remain dry. The building survives. The oldest surviving stave church, Urnez, built around 1130 AD, shows no significant rot in its sill system after nearly 900 years. The corner posts. The most impressive engineering appears at the corners. Each corner of a stave church features a massive post, typically 12 to 16 inches square, rising the full height of the building. Into this single post, all the horizontal framing members connect. A single corner post at Borgund receives connections from 4 ground sills, 4 wall plates, multiple intermediate girts, diagonal bracing members, roof framing connections. Each connection is a separate joint: mortise and tenon, dovetail, or pegged lap joint. Each joint is cut to fit that specific location, accounting for wood grain, load direction, and expected movement. Modern structural engineers analyzing these connections find load distribution that approaches mathematical optimization. The Vikings achieved through iteration what we calculate with computers. The wall planks between the corner posts. Walls consist of vertical planks set edge to edge. These planks don't simply butt together. Each plank has a tongue on one edge and a groove on the other. The tongue of one plank fits into the groove of its neighbor, and this tongue and groove system allows the planks to expand and contract with moisture changes while maintaining a weather-tight seal. The wall breathes but doesn't leak. At top and bottom, the planks fit into grooves, cut into the horizontal sills and plates. No nails. The weight of the structure holds everything in place. The roof system stave church roofs present the most complex joinery. The typical roof system includes principal rafters meeting at a ridge beam, purlins running horizontally across the rafters, scissor braces providing triangulation, multiple layers of boarding and waterproofing. Every connection is a wooden joint. The scissor braces, crossed diagonal members that prevent the rafters from spreading, connect through interlocking half-lap joints pinned with wooden pegs. The geometry of these connections transfers roof load down through the posts to the foundation without creating outward thrust on the walls. This is sophisticated structural engineering, achieved without written calculations. The decorative carving, perhaps most remarkably. All this structural complexity was achieved while incorporating elaborate decorative carving. The Urnez church features portal carvings of interlaced animals and dragons cut directly into structural members. The carving doesn't weaken the structure. It follows the grain, removing wood that carries no load. This required carpenters who understood both structural engineering and decorative art. The same person who calculated joint angles also carved serpent heads. This is structural engineering masquerading as decorative art. Of approximately 1,000 stave churches built, 28 survive. The other 97% were destroyed, not by rot, not by structural failure, by us. The demolition century between 1650 and 1850, Norwegian communities systematically demolished their stave churches. The reasons were multiple. Population growth made the small medieval churches inadequate. Congregations needed larger buildings. Changing architectural fashion favored the new styles coming from continental Europe. Stave churches looked primitive compared to Baroque stone cathedrals. Reformation theology rejected elaborate decoration as Catholic excess. The carved dragons and interlaced ornament were seen as pagan remnants. But the primary driver was simpler. Nails became cheap. The Iron Revolution. Before the Industrial Revolution, iron was precious. A single iron nail required hours of blacksmith labor. Buildings used wood joinery because metal fasteners were prohibitively expensive. Industrial iron production changed the economics. By 1800, machine-made nails cost a fraction of hand-forged ones. Suddenly, any carpenter could build quickly by nailing boards together. The years of training required for proper joinery became unnecessary expense. The skills stopped being taught. The master carpenters who could cut a proper dovetail were replaced by laborers who could swing a hammer. Within 3 generations, the knowledge was effectively extinct. The knowledge loss. When Norwegian authorities finally recognized the cultural value of stave churches in the mid-1800s, stopping the demolitions and beginning preservation, they discovered a problem. No one knew how to repair them. The joinery techniques had been out of practice for generations. Carpenters could see the joints, but couldn't replicate them. The tools had changed. The training had disappeared. The intuitive understanding of wood behavior was gone. Early preservation efforts actually damaged churches by using inappropriate modern techniques. Nails were driven into joints that had survived 800 years without them, creating new failure points. Only in the 20th century, with systematic archaeological and engineering study, did understanding begin to return. The modern recovery today, a small number of specialists practice traditional Scandinavian joinery. Schools in Norway and Sweden teach the techniques. Preservation projects employ craftspeople trained in historical methods. But the number of people who can build a proper Viking-style structure from scratch is measured in dozens worldwide. The knowledge that was common among thousands of medieval carpenters is now rare expertise. We traded skill for speed. We gained efficiency and lost resilience. A nail-built structure can be erected by minimally trained labor in weeks. A traditional jointed structure requires years of training and months of careful work. But the nail-built structure will need major repairs within 50 years. The jointed structure will stand for 500. We've chosen the cheaper option and accepted the hidden cost. Nor the techniques haven't completely disappeared. Japan. On the other side of the world, Japanese carpentry preserved nearly identical principles. Japanese temple construction uses wooden joinery almost indistinguishable from Viking techniques. Mortise and tenon, dovetail, scarf joints, wooden pegs. No nails in traditional structures. The reason? Japan also lacked cheap iron historically. The same economic constraint produced the same technical solution. Japanese joinery masters, miyadeku, still practice today. Their training takes a minimum of 10 years. They use hand tools that would be recognizable to a Viking carpenter. When Norwegian preservation specialists need to understand how a particular joint was cut, they sometimes consult Japanese masters. The techniques are that similar. The timber frame revival. In North America and Europe, timber frame construction has experienced modest revival. Modern timber framers use power tools for rough shaping, but often cut joints by hand for final fitting. The principles: wood selection, grain orientation, joint geometry, derive directly from medieval practice. A properly built timber frame house today can match Viking longevity. Structures from the early American colonial period, built with traditional joinery, remain sound after 300 years. The knowledge exists. The barrier is economics, not capability. What it would take to build like the Vikings built, modern construction would need to accept. Longer project timelines. A jointed structure takes 3 to 5 times longer than nailed construction. Higher skilled labor costs. Joinery requires trained craftspeople, not general laborers. More expensive materials. Proper joinery requires quality lumber, not the fast-grown knotty boards that fill modern lumber yards. Different maintenance expectations. Jointed buildings need different care than nailed buildings. Periodic inspection of wood condition rather than fastener replacement. The total life cycle cost might actually be lower. A building that lasts 500 years costs less per year than a building that lasts 50, even if initial construction costs more. But modern finance doesn't think in centuries. Mortgages span 30 years. Building codes address 50-year lifespans. No one budgets for 500. The Vikings built for their grandchildren's grandchildren. We build for the next owner. A carpenter in 1180 Norway stood over a corner joint he'd been cutting for 3 days. The notch had to be perfect. Not close, perfect. His teacher had shown him the technique. His teacher's teacher had refined it. 7 generations of accumulated knowledge flowed through his hands into the wood. He didn't think about structural engineering. He thought about fit. He didn't calculate moisture expansion coefficients. He knew that green wood shrinks and the tight joints get tighter. He didn't reference building codes. He followed traditions that encoded centuries of structural wisdom. And when he finished, when the log settled into its notch with a satisfying thunk, he knew it would hold. He was right. Today we drive nails by the thousands. Pneumatic guns sink fasteners in milliseconds. A house goes up in weeks. And in 50 years, those nails will be loose, those walls will be sagging, and someone will decide it's cheaper to demolish than repair. The Viking carpenter's joint is still tight. The physics hasn't changed. Wood still moves. Moisture still cycles. Geometry still locks. What changed is what we value. The Vikings valued durability because they had to. Resources were scarce. Labor was precious. A building had to last because building again wasn't an option. We value speed because we can. Resources are cheap. Labor is expensive. A building only has to last until the loan is paid off. The Vikings didn't fasten buildings. They interlocked them. 28 stave churches stand in Norway. Each one is a monument to knowledge we've chosen to forget. The techniques are documented now. The tools can be replicated, but the training can be revived. The question is whether we want to build for 50 years or 500. The geometry will be there when we decide. If you want to see how Vikings applied this same precision to the survival systems that kept them alive on open ocean crossings, building warmth without walls, watch the video on screen now. The thermal engineering is as sophisticated as the joinery.